Okay. So the current topic we will look into is expanding context length in LLM. Now, what is the problem with the larger context length? We will first look into it. There are three problems that I noticed. The first one is insufficient memory, then increasing training time, and the third one is dependency on certain positional encodings. So why the insufficient? I mean, how the memory is? I mean, insufficient uh, because it's due to the lack of the memory space in GPU. Currently, we don't have any. I mean, GPUs in TBs, unlike CPU RAM. So the self attention has n square space complexity. So when we calculate the attentions, attention matrix here, it will have a n square uh, space complexity. That means if we have input tokens of 100, so we have 100 input tokens, then it will have 10 raised to power 4 uh, space complexity. That means it will take 10 raised to power 4 amount of space and multiplied by the whatever the bits are. Say we have 32-bit float, then 10 raised to power 4 multiplied by 32. But nowadays, we want our memory to be somewhat 100K, something like that. Now, if you square that number, it will be a very huge number, and maybe it won't be fit in a 32-bit GPU, only that attention matrix. So, say for example, we have the basic LLM models has a 4K, has some has 4K context length, and we want to increase it to 8K. Uh, so the attention matrix will be increased from 16K to 64K, which is almost the 4 times of that. Just for doubling our context length, we need 4 times of the space. So that's one of the issues with increasing the context length, a memory issue. Then increase in the training time. Uh, when training our model remembers the context size given during training. So when we give for example, a model is trained on 52 512 tokens, 512 tokens, and in during inferencing we are giving it let's say 1,000 tokens. Then the perplexity of that model will be very worse. We can see here during sinusoidal, that is absolute positional encoding and rotatory positional encoding, the perplexity worsen. So this is the graph from the alibi paper. We won't be
So just one
going.
question here, Amod. So, like these plots suggest that whether it is a relative embedding or relative positional embedding, or it is absolute one, in all the cases, the performance will degrade, right?
Yes, but that's only the case when the model is trained on 512 tokens and we are giving more context size
Matlab,
than what is
whatever
trained.
it has been trained on, if we give more than that, then performance is more likely to be degrading, right?
Yes, right.
Okay, fine.
So that's what they have said. Hence, when training our model for a huge context length, we require a huge data set and time with it because we are training on a huge context length. So now there is a certain dependency on positional encoding. So in case there are some pre-trained absolute positional encoding, we won't able to increase the context length without retraining that positional encoding. That's a small thing on that positional encoding. So any question still here? What I mean, any someone want to add anything else that what will be
Uh,
the disadvantage?
Amar,
Yes, please.
I was just wondering कि let's say कि हमारे पास अगर मेमोरी का इश्यू है right?
Yes.
तो जैसे कि let's say कि हमारा तुमने बोला कि 10 की पावर 4 का मैट्रिक्स हो जाएगा. So
हाँ.
let's say कि we use some technique to let's say compose this matrix into a smaller matrix.
Mhm.
And जैसे कि let's say कि 10 की पावर 4 है तो अगर let's say उसको 3 या 10 की पावर 2 भी अगर लेके आ जाते हैं like using some let's say SVD या फिर ऐसा कुछ techniques. And then use
Uh,
that thing in as our let's say कि the input let's say like understood मतलब.
yes, yes, I understood. But what will that do is increase our computation a lot. So हम लोग ने चलो इसको कम भी कर दिया ना. So we require this attention matrix again and again, just because we have to multiply this with the V matrix. So so we are not talking about 10 raised to power 4. Here we are talking about something 100K. 100K, I want the 100K context length, something like that. Or 10, let's say 10K context length, which is let's say we want a 10K context length, and just multiplying it, it will be something like 100K attention scores. Sorry, 100 million. अगर मेरे को 10K कॉन्टेक्स्ट लेंथ चाहिए तो मेरा अटेंशन स्कोर विल बी 100 million, विच इज वेरी ह्यूज अमाउंट. सो एक जीपीयू में रखने का, देन सीपीयू में स्वैप करने का, this takes time, very huge amount of time, just for my single inferencing. So this thing we don't want like that. So in the going ahead session, I mean in this session, I am talking about two papers, which will do a long context inferencing without taking that much time. Is it clear?
Yes, yes. So just one more clarification needed here. Amod, so you meant to say that, see, whatever context length we have trained a model on, we can always increase the context length at the time of inferencing. That is all possible, right? But
Yes,
performance will degrade, and we might require more memory also to store these attention weights, attentions.
yes, right.
Right. Okay.
I
Chief.
just have a small clarification on Himanshu's question. So I think Himanshu was asking like, what if we decompose the matrix to a smaller matrix? So Himanshu, I mean, that is essentially so every cell in the attention matrix is basically a score between two specific positions, right? So
I
there are
believe
some.
he, he meant chunking, right?
Yeah,
I
exactly. So
mean,
I was coming to that. So we can have some, so there are already like techniques which compute instead of the entire attention matrix, they will compute like a sparser matrix. So they will say that, for example, after a window of size K, we'll have all the attention scores as 0, which is essentially saying that, okay, I won't attend to tokens beyond a certain context, and then they'll introduce some sort of global attention score or local attention context. So they are basically able to scale it to a larger context size. But again, the matrix, so most of the long context models which initially came up, they were trying to sparsify the matrix, the attention matrix.
अच्छा. And then it's like initial intuition to use a solution.
Hmm.
Correct.
Okay, going ahead. So there is one paper.
Just one more question here. Go to the
Yes,
previous slide here. So what about the LEB? LEB, the perplexity is still the same, even though we increase the inference length, right?
uh, yes, that's what they have given. So in this session, we won't be going to LEB, because I need to check other papers also what they are thinking about LEB also. But yeah, that's it. I mean, they are saying that okay, our perplexity won't increase that much for a long context input, but that I need to check on other papers also, that what
Sure.
they think about LEB.
Okay. Okay.
Yeah. Then there is a paper, long context language modeling with parallel context encoding. Uh, it's from the Princeton University. I think it's my current favorite paper. So the abstract, in abstract, they have given that they have introduced context expansion with parallel encoding. They termed it as CP. applied to existing decoder only LLMs. So on decoder only LLMs, we can apply this technique on for extending the context window. So what the CP does is they add some small encoder to process input chunk by chunk. And so what they does is they add context, they add encoder. Generally, it makes decoder only LLMs to a encoder decoder LLM. So by adding the encoder and cross attention matrix. Then they have said CP extends the context window of Llama 2 to 128K tokens, offering 10 times the throughput with only 1/6 of the memory utilization. So what they meant is that their technique, when applied to Llama 2, for 128K tokens, will consume 1/6 the memory and give 10 times the throughput. That's what they mentioned. So
Oh, just
let's
one second. What do you mean by throughput here?
the speed. I mean, giving the input, and I mean the speed in which we are getting the output. Inferencing speed, we can say. It will
Sure.
give one by one tokens, right? So that's what I think about the throughput.
Also, Amod, so this 10x increases in comparison to the smaller context Llama 2 model, or is it if we had trained like a 128K context model Llama?
128K.
Acha, okay.
It's not about smaller.
Okay.
So we will just revise a cross attention and encoder decoder models, how it generally works. So here in green, we are seeing encoder side, and in pink, we are seeing a decoder side. We give we give input X to the encoder layer, having self-attention, add normalize, read forward, and add normalize. In classical decoder architecture, we have self-attention, add normalize, and the extra thing here is encoder decoder architecture attention, which we also call it as a cross attention, and the rest are the same as the encoder, that is feed forward and add normalize. So in encoder decoder, the output of the last layer, that is encoder 2 in this case, so not the output, the K and V matrix for of the last layer will be given to all the encoder decoder attention, that is the cross attention. Uh, and the query matrix will be from the decoder side only. I hope this is clear.
Amod, like, sorry, can you just repeat एक बार फिर से कि like how do they do it?
So when we give the input X to the encoder, we will every self attention has a we calculate K, QK, and V matrix, right?
Oh,
From
अच्छा
the
अच्छा अच्छा अच्छा.
from the last layers K and V matrix, we take the last layers KV matrix and give it to the decoders, encoder decoder attention or the cross attention. So this KV matrix is going to the encoder decoder attention.
Fine, 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 fine. Okay,
So what CP says is this is my what CP says, this is my original llama model in the dotted right hand side they have given, and we will be adding a cross attention here. In the last slide we say the name as encoder decoder attention, but it is also called as cross attention. we will add the cross attention here. We will take encoders, multiple encoders. So in this case, we have taken Robota, uh, and we will be giving the input to those encoders. So first chunk of the input is given to the first encoder, then second, and then third. And the last chunk will be, which will be the main portion of our context, will be given directly given to the llama model. The output of this encoder, uh, namely a phi 1, phi 2, and phi 3 till phi n, will be concatenated and then given to the cross attention matrix. So so during training or fine tuning, this whole model, we just need to fine tune the encoders and cross attention. So here they have given,
Sorry, I'm interrupting. So
yeah,
this we are concatenating all the embeddings for different additional context chunks, right?
yes,
So, but this might have different like variable vector sizes, right? Depending on number of context chunks we have, right?
no, why it will be having a different. So let's say this is taking 512 input.
Hmm. I mean, the
Uh,
output would be a 512 dimension vector for
yes,
say each of the tokens in the context, right?
yes, right. So I don't got the question.
So I'm asking that suppose I'm passing some paragraph to this encoder, okay? So its output would be, I mean, for every token, I can get a vector, right?
Yes, yes.
So then this would be a 2D matrix. Then again, for the second context also, I'll get a 2D matrix. Then how exactly are we concatenating? And then say in some case, we might have only 3 contexts. In some case, we might have 10 contexts, right? So
But
then the second.
these contexts are continuous, right? So this is
Hmm.
the chapter 1, chapter 2, chapter 3.
Hmm.
So say this is the n dimension, then
Hmm.
it will be, so let's say n1, n2, n3, then we
Hmm.
will be concatenating n1, n2, n3. So this is my n1, okay? Then I
Hmm.
will be having n2 here, like this, and n3 will be like this. And
So first question is ki N1, N2, and N3 all might have different sizes depending on at max they might have 512 tokens, right? So
yes,
and whatever is the embedding dimension of the encoder, suppose that is D. So at the end, if we have like say 3 contexts, then we might end up with a 3 into 512 cross D type of matrix, right?
right.
Okay,
So
and suppose in some other case, if we end up with say 5 contexts, so then in that case we'll have 5 into 5 and 2 cross the matrix, right?
yes.
So
So by context, what exactly you mean? You mean the encoder?
matlab the number of chunks which have been individually passed to the encoder.
Yes, if we have 5 chunks, then there will be a 5 uh, that blocks. That is n1, n2, n3, n4, 5, n5.
Okay, and then how is this variable length matrix passed to the cross attention layer? I mean, what exactly is passed and where?
Okay, we will see in the next slide. I will.
Okay.
They are given some equation. We will see it.
Okay. And one last question. I think, I mean, this is probably very trivial, but this
Huh.
is the same encoder. We are reusing it multiple times, right? Or
Yes,
are these
of course.
different copies?
No, we are using the same encoder multiple times. If we
Okay.
use the different copies, then it won't able to satisfy the 1/6 the memory.
Right. Makes sense. Okay. Okay, thanks.
Okay, so this 5152 concatenate and we get a bigger phi and then given to the cross attention. In the next slide, we will see the equation what they have given exactly. So they are saying that we have context length of x1 to xt. So the first M tokens, that is X1 to XM, will be termed as additional context C, and the last tokens, that is T minus M, which they termed as N, will will be the main input X. That is, it will having the main question. Then they split this X1 to XM into chunks, C1, C2, C3 to CK. So they have defined encoder as MENC to donate, to denote the encoder model, and DENC or MDE to denote the encoder model with the embedding sizes DENC. And similarly for the decoder model, MDEC and their hidden sizes DDEC. And similarly, what I mentioned in the last slide, that they are sending these chunks to the encoder, multiple encoders, and then concatenating to get the phi here. So yeah, these are just the dimension of this phi, what the dimension of the phi will be. So as per the Shruti ma'am has asked in the last slide, that what will be the what will be number of tokens, how will be the number of tokens merge. So like here they have mentioned the size of the phi, the darker phi will be M, which is the number of input tokens that we have given. I hope this is clear. Hmm.
So is the hidden dimension of encoder and decoder supposed to be the same?
No, they have used an wait, they have, I think there is a text. Oh yes, up projection that transform the DENC model, DENC dimensional to DDEC. So they are using a matrix to transform that lower dimension to higher dimension.
Acha, so when
So
we concatenate, the dimension would be M cross D encoder, and then we up project it to M cross D decoder. Is that right?
uh, now that you have mentioned, it should be something like that. But what they have given is when we have the output from our encoder,
Hmm.
we will then convert it into DDEC as what they have given from here.
Oh,
So they are already doing the up projection.
oh, acha. So this is including the up projection. Okay.
Yes.
But then
Hmm.
M encoder is just the encoder, right? So maybe
Yes.
they have included it somewhere in the encoder part only.
I think they have made a mistake here. So this ideally should be D encoder,
Hmm.
right? And
Yes,
that
it
D,
might. Mm.
and then there might be another weight matrix through which this matrix is passed, this phi is passed, which converts it into D deck. But this is
Uh,
something which is not explicitly mentioned here.
yes, but if we can do it, apply the projection matrix in encoder also, but they haven't given something like that, where they exactly apply the projection matrix, where it is in decoder or in the encoder side. So any other questions? Okay, going forward. Now they say that CPE is efficient.
Amod, sorry,
Yes,
could you go back to the previous slide? I'm just trying to understand what they are saying. So they are saying that this phi is provided as keys and values to the cross
yes.
module, and the hidden state of X as queries. What was X? Sorry.
To construct the cross attention. Okay, X is our input.
Oh, acha, the final input provided to the decoder.
Yes, this is the main X. So no. So what we do is, let's say we have a huge context of the T tokens. What they have mentioned, we have huge context of T tokens. So the
Basically,
first
right?
mm, the first M tokens will be this chapter 1, chapter 2, chapter 3,
Okay.
and the last remaining token will be our main question. What should be the question of who betrayed, something like that.
Okay.
It will be our input. That is, I think the llama 2 is 4096 context that. So this will be the 4096 last token, and this X will be given to the decoder. And
Right.
as you know that in cross attention we use the Q query matrix from the input side. So if we give the X as an input to this decoder, the query matrix in the cross attention will be of the X multiplied by the query weights, and
Ah,
the K matrix will be from the encoder, and K and V matrix will be from the encoder. That's what they mentioned.
actually just trying to understand कि मतलब for different inputs the size of this phi after concatenation would be different, right? So
Let the size of the phi be say 500 or maybe 512. Yes, it will be different, but it will be making the attention matrix as M into N, right?
no, sorry, can you repeat again?
So let's take an example. The phi is 500, and our input is something like 100. When we are making the attention matrix, it will be I believe it will be 500 into 100 or 100 into 500, depend.
अच्छा सॉरी एक और चीज
हाँ.
तो no sorry so you were saying that this m is kept as constant, yeah, sorry, what were you saying? M variable m कैसे how will we?
So M can be variable, I'm saying. M can be variable, and N is of course the constant. It will be 4096, and M can be variable.
Okay, huh. And then we end up with this phi matrix, which is m cross d decoder somehow. Suppose like after up projection, it is of dimension m cross d decoder, and then so then if we have a variable m, how
Mhm.
are we exactly keeping? I mean, giving that as keys and values to the cross attention module.
So let's say this case is M cross D.
Hmm.
I'm keeping the D as DEC, that is decoder embedding dimension,
Okay.
and then queries will be N cross D, right?
Hmm.
Then the matrix, attention matrix we will be getting will be N cross M, right? Because Q multiplied by K transpose, right?
Honey, but this is for just one input, right? If we have a different m, I'm just trying to understand कि मतलब the value of the, I mean, जो भी हमारा वेट मैट्रिक्स सॉरी वेट एंड जो की मैट्रिक्स है उसका साइज
Hmm.
कैन नॉट चेंज राइट फॉर डिफरेंट इनपुट्स अदरवाइज वी वोंट बी एबल टू बैक प्रोपगेट राइट
It will be the multiple of 512. M will be the multiple of 512 if you want to think like in that way. So because the size of this my encoder is 512, I actually did not understand the question. Can you please repeat it again? I mean, I don't understand the issue or what exactly the issue is. So we will be getting here M cross D. This is the phi. The size of the M is keep changing. I don't understand what exactly the issue is here.
हाँ तो आई एम सेइंग दैट व्हेन वी आर पासिंग सम वन इनपुट टू दिस entire architecture,
Hmm.
this M is, for example, just 512. Okay, so and this means that there is just one chunk and only once the encoder was used. Okay.
Yes. Okay.
Then suppose in the second run we have like 2056 cross D, which is like
Hmm.
4 times 512. So we have 4 chunks.
Yes.
So
ठीक है.
I'm just trying to understand ki will this, I mean, will the entire architecture will still be like, can we back propagate through these different dimensions at once?
Yes. I mean, when we will be we can back propagate because it needs to back propagate from here and then here also from the both the end. So I mean, you are saying that what will happen if we first our M is this at the inference one, our M is 512, and at the second inferencing we are keeping N as 4 times 512, right?
Because this is like a huge difference, right? Even while training
But
the regular
but our
transformer,
encoder
we
is
have
same.
नहीं encoder तो is same, I agree, but I'm saying कि तो usually जब when we have variable context lengths, तो usually it will be limited, right? Because अगर 4096 है तो we'll only have chunks which are less than 4096. But यहाँ पे तो we'll have like multiple possible options, right? So
Yes.
just questioning कि मतलब
The
even if
worst
variable, हाँ हाँ.
the worst case scenario will be our cross be able to calculate properly, but
हाँ,
there
मतलब
won't be.
how will it be stable enough?
I mean, you are saying that output will be good or something like that कि output बराबर होगा कि नहीं होगा.
हाँ.
That they have said कि for the long context it's giving okay output as compared to llama 2 if it is asked for a long context. That's what they are saying.
अच्छा.
So they haven't, I mean, guaranteed कि मेरा जो output है इसका will be as good as the llama 2 in 7 billion, sorry, in its own context range. So my llama 2,
Their context, okay.
हाँ, मेरा llama 2 अगर 4K है and मैं ये same use कर रहा हूँ for 4K, then they haven't been, so for that they haven't shown anything like that.
अच्छा, okay. And one more thing. So there is no restriction on number of context, like individual context chunks that we can have, right? Or is there a
uh,
limit?
Technically there is no restriction on number of contexts. We can take as many as we can,
Hmm.
um, but the memory should uh, I mean there will be memory issue if we are calculating this n cross m. So as long as you have enough memory, we can have as many as much context we can.
अच्छा, ठीक है, okay.
But yes, your I mean doubt is valid. Ki will this cross attention will able to give the correct output or the good output for the huge context length. I hope it is clear.
हाँ हाँ.
Otherwise, you can just put it on Excel and we can discuss later.
हाँ हाँ, I think we can go ahead for now.
Okay.
Acha,
Now,
just one more question here. So how do you create key and value from 5?
no, it's already created. We don't create the key and value. So they
Okay.
haven't mentioned the we it's a phi including key and k and v. It has k and v.
No,
They have
see,
just termed
once
it as phi.
no, that is okay. But see, when you are using an encoder, right, at the top, you are going to get one vector corresponding to one token, right? So do you multiply with some key and value matrix at the top to get key and value corresponding to a given token? And then you create two phi, one for keys, one for value.
No, I believe this is from the standard encoder, and I think that they will be just getting the key and value from the last encoder.
No, so see, encoder output doesn't give you key and value,
No,
right? It just
encoder
gives
self
you one.
attention. I'm
No,
talking about self attention.
self attention is okay, but encoder like self attention is the lower layer, right? After above it, you have the feed forward layer,
Yes,
right? So the output from the feed forward is for each token a single vector,
right. So
right?
there
And then
might
you
uh,
multiply this with key and value vector matrices at the top.
yes, it might be that case also. We can do both the ways. I mean, it will be the only same, just that we won't be having feed forward and add normalized layer up ahead.
Okay, so which encoder they have used here? Is it the
Roberta.
standard Roberta they have? Okay.
Actually, I now have another doubt. I was actually abhi tak thinking कि maybe they are directly using the phi vector as key vector and the value vector, because if the dimension of phi is changing, then ideally we cannot change the dimension of the WQ and WK and WV matrices, right? Because that will stay the same. What we can change is the key vector ka size and value vector ka size depending on the context length. But then in that
Yes,
case, actually, I missed thinking ki what exactly is even the learnable parameter यहाँ पे then.
the learnable parameter will be whole Roberta model. So,
मतलब so just to clarify, so इस cross intention module में we won't be learning the key and the value matrices, right?
we will be, sorry, no, we won't be learning key and value matrices in the cross notation.
So okay,
Just
so and what about the query?
we will
That
be learning that.
it sounds very complicated कि we are not learning. ठीक
I
है.
mean,
Just learning the so okay, so just to be clear, self attention में will learn all the matrices, and
yes,
cross attention में will only learn the value matrix query matrix WQ, and key vectors and key vectors and value vectors will just directly take as the output of phi, right? We'll just copy it. We won't be having a weight matrix for WK and WV, right?
yes, I believe that to be the case. I just need to check once again because yeah, I sh that's to be the case. I believe that we just copy and paste. We don't calculate it again, but I'm not sure about it.
ठीक है, okay.
I will let you know about that case.
Okay, ठीक है.
Okay. Now the efficiency with regards to KB cache. So what they say that so we have m plus n tokens total, and it reduce memory consumption by avoiding the caching of m plus n multiplied by L key value pairs. Here L is the number of layers. So in the standard decoder only architecture, uh, we uh, we have the key value we have key value cache as separate matrix to store the k and v values of each self attention layer. uh, so it will take this amount of parameters to store in the standard decoder. They have given here the standard decoder will require this amount of parameter multiplied by their embedding dimension, which is DDEC. Now, in their case, they just required M multiplied by DENC plus NL multiplied by DDEC. Now, this is the memory they require to calculate this. This is just a memory. So they won't be storing the MDENC in the KV cache. They will be just storing this N into L DDEC. I hope this is clear.
अच्छा आमोद, why? Sorry, could you explain again कि ये MDENC जो है, we don't need to store it. Why?
Encoder. This is the encoder side. For encoder, we don't store KV cache because encoder does not need to give its output to its input again and again.
हाँ हाँ, मतलब
So
I mean, okay, so I'm probably asking just this one thing, that this MDENC is the same 5 vector which will copy for all the layers, right? So we are just saying that we don't need to have separate L copies of it for each layer, right? And we'll
yes,
just store one copy of phi 5.
yes. So the L here, what it means ki we store in KV cache.
Hmm.
So we store for each layer while storing in the KV cache. Say this is my decoder. Let's say we have 2-layer decoder. For this layer, we will store in K and V. For this layer, we will store in K and V again. So what is the maximum value we have to store is n times the number of layers. This is the maximum value we have to store. But in case of encoder, let's say this is my encoder one, the first layer of the encoder. This is my second layer of the encoder. Okay. And when calculating the self attention, we need K, V, and Q also. Okay. So we will, for just for calculating the self attention, we need to store these values in the memory. And after that, after we get its output, that is X, after we get this output, we can just ignore this. Uh, Whatever we have stored in the matrix, we can just delete it. We don't need it any further. And again, for the second layer, we again recalculate it. So hence there is no L here. L for the MDENC. I hope this is clear.
हाँ हाँ, understood.
So, acha, just one thing again, I'll just present whatever you said in a different way, right? So
Yes.
at the end, like once you have encoded all the M tokens, right? So you just need to store key and value for those M tokens,
Yes, correct.
right? That's why you have MDENC, right? And then
Yes.
whatever you have at the decoder side for them, you have to store the KB.
No, no. For MDEC, it's just this is what they have saying the memory utilization.
Yeah, so this
Let's
is just
see it like that.
yeah, so this is not for per layer of decoder. It is like you have to store only one copy of this KV for which are coming from the encoder side
Uh,
at the top.
at that specific point, this is actually not a KV. Just during calculation of self attention, we do Q multiplied by K transpose, right? At just that time, this Q and K will be in our memory, GPU memory. What they are saying ki, to calculate the self attention, Q and K needs to be in our GPU memory to compute the matrix multiplication, and therefore it will take some space. That's it. It won't be a KV cache in the encoder side.
Hmm.
The KV
Fine.
cache will be only on the decoder only.
Yeah. Yes, sure.
Okay. Any other questions?
अच्छा,
Uh,
they are also saying that this decoder का dimension is much greater than encoder dimension. Uh, just wondering like what values they have used.
so I believe the for Robota it's 512, the encoded dimension, and for the Llama 2, I believe it's 400 and 4096.
ठीक
I
है.
just need to confirm these values. I have
हम्म,
read some months ago.
हाँ, I think that's relatively okay.
Okay. Now the training data set they have taken. So they said we
One more question before we go to the. Do we have any more training details coming here in future slides?
No, there won't be in training details means the evaluation.
नहीं नहीं. So okay, I'll ask the question directly. So I was thinking कि so suppose यहाँ पे what we are doing is कि for the decoder we'll try to generate the next token in the like next token in the sequence. And eventually वहाँ पे तो I can understand कि वहाँ पे will compute the cross entropy loss and everything. How exactly is the encoder trained? Because you said encoder would be trained, right?
Yes, it is like a fine tuning thing. They haven't such given ki how they are training the encoder with LoRa, with QLoRa or something like that. Or maybe I haven't seen it clearly. But they just have given that we are training our encoder. So we can apply anything to the encoder. Like
Actually, my question is कि तो for example, when we are training a simple bird type model, तो वहाँ पे तो we can do something like masked language modeling, right? But वहाँ पे वहाँ पे we know what
so
is the
you are
loss
talking about
function.
pre-training, right?
No, not pre-training. I'm asking कि encoder में whatever updates we are doing, how will that happen? मतलब वहाँ पे what exactly are we doing?
So the encoder's update will be directly from the output. I mean, the output given by the llama will be backpropagated to the encoder also.
हाँ,
So
so that's what I'm asking कि what exactly will we backpropagate? Because यहाँ so decoder में तो I can understand कि cross attention module में will only have the WQ वाला matrix which we will be learning. Self attention में all three matrices, feed forward में all the parameters because we can like write it eventually वो loss function के terms में ये सारे matrices, right?
hmm.
But how
So,
do we translate that P के terms में encoder के parameters? Because
so we
यहाँ
have
पे
the K matrix here and V matrix here, right?
which is just a direct copy of the vectors, right? So
So the copy is coming from this eventually. So when we have an encoder and decoder models, I believe it should able to backpropagate to encoder also. I currently don't have the equation. If I got the equation, I will let you know for sure that
ठीक है.
कि how exactly, or if I got any what we say, if I done some practical on that, I mean the replicate their model, I will let you know.
ठीक है. Also, do they like have they written the code from scratch or because I think I'm seeing it just now that the feed forward and the self attention layer is frozen. So then I think it's relatively easier because we just have the encoder wala parameter in the.
Yes, encoder also their robota, so they don't have to write code for the encoder. They just have to add the cross attention, and they have created some function or class. I think yeah, there was a cross attention function in
Hmm.
their code, but
अच्छा.
I haven't seen the inside of that function. It's just the initialization of that function I have seen. So
ठीक
I
है.
don't exactly know the working of that function.
ठीक है. Okay.
They have given their code in GitHub. So
अच्छा ठीक है. Okay. Thanks.
okay. For training data set, data set, they have used Red Pajama, which is a training corpus. It is the open source reproduction of the Llama 1 training data. It contains 1 trillion tokens from the 7 domains: archive, books, C4RP, CC, GitHub, Stack Exchange, and Wiki. For the they have used only a 1% of this data set. Sorry, 1% of this data set, uh, something like that they have used. So, for example, Llama was trained on some 100%, then they just trained this on 1% of that what the Llama has trained on. And then they were talking about CEPED, which is the unsupervised training. They just have given a short brief of that. They haven't mentioned much about it. So what they are saying that we can make the decoder model act as a teacher, and the whole encoder decoder, what that is CEPED model, as a student, and we can then learn our weights using this student teacher model. That's what they have given. And here they have given evaluation. So for 4096 tokens, uh, so for 4096 tokens, it just, I mean, they are just showing that it works similar to what Llama 2 is working. For a greater tokens, 8K tokens, the Llama has a poor quality. And say for the 32K tokens, again, it is CP is working a little better than Llama 32K. They haven't taken Llama 2 because for 8K only they are getting poor quality. And for more than 100K tokens, uh, Llama 32K and Yarn 64K were not working quite good. But their CP and streaming LLM are working, and even using a less amount of memory, as mentioned here. Any questions? And I think sir has asked the what's the throughput, number of tokens per second. Okay. So shall we move ahead? Okay. So during evaluation, they have evaluated on NQ, TQA, and POP QA datasets. This is the example of trivia QA dataset. Uh, we are given the question, and the answer is just a one or two words. So they have evaluated on this, and they are getting good results as compared to Llama 2 and Llama 32K. So any questions in the CEPE? Otherwise, we will move to the next topic.
And just one clarification. So यहाँ पे if we have say k equals to 60 for ये for the CEPE वाला SEPE model,
Yes,
we'll just use the last 10 in the decoder and the rest will go in the encoder, right?
last 10 in the decoder, and yes. I mean, depending upon the context size. These are the just number of retrieved passages. Okay.
Okay.
So it will depend upon the context size. If my last 10 have 4096 context size, then yes, it will be going to the decoder.
अच्छा, so I'm assuming 20 paragraphs it could fit, right? Because Llama 2 may we are doing this experiment with k equals to 20, right?
Yes. So 20, yes, it will be fit till 20 paragraph, something like that. Uh,
And what are these values? Is this like accuracy or?
yes, this is the matching score. That is, if my CP has given the this same sentence or the words, then it just the score for that.
Oh, अच्छा.
कितना मतलब मैच हो रहा है, exact matching.
So this would be 1-0 जैसा case क्या? If the answer exactly matches, it's 1, otherwise 0.
Yes, I believe, but I need to confirm that.
अच्छा, okay. Also, do you think the values actually show बहुत significant difference?
No, I don't think the value is showing the significant difference. But the point is that we can have very huge context length using this technique. In some cases, for the 100K context length, Llama 2 fails
Hmm.
miserably. So if someone wants to have a 100K context length with only for using Llama 2 in less amount of time, then this technique is good for them. That's what I think.
Hmm. अच्छा, okay. Oh, so these values are perplexity values. ठीक है, okay.
Yes.
And maybe the other data sets जहाँ पे we were seeing the numbers, they are not suitable for long context, yeah, कुछ the natural
So
question वो वाला data
I
set.
think they haven't taken enough long context. We cannot say for sure because for Llama 2 they just stop it at 20 paragraph,
Hmm.
and for Llama 32K 60. But we are not sure how many tokens are this. Is 60? That's we are not sure about.
Hmm. And also, if like, do we actually need these many paragraphs to answer the question? Maybe it's found in the first 20 or 30 paragraphs only in most cases. So we might not see better numbers, significant difference. ठीक है, okay.
Yes, we can also use RAG if you want to get the specific paragraph, but it
Hmm.
depends upon the use cases.
हाँ, actually, RAG would have been a better baseline, right? यहाँ पे.
Yes. So this replug thing is similar to RAG only. This is also for the long context.
अच्छा, but यहाँ पे
In
they have done it only till 30 paragraphs. तो.
yes, in this yeah, they can take a 30 or anything. What this thing does is it gives it also has an encoder. It like a RAG based encoder. I mean for the RAG. So for using that encoder, it will get the embedding matrix and then compare this code.
अच्छा, okay.
And for each score, they will calculate the probabilities and add those probabilities and give you the answer.
अच्छा,
That's
अच्छा.
something.
ठीक.
Okay. Uh, so anyone else have any question in CEP? Okay, then let's move it. So efficient streaming language models with attention sync. This has been made with MIT, Meta, NVIDIA, and other universities. So this is, I mean, you might see this research has already been done, or some research has been already done. But what they have done is, yeah, they have brought various research together and just shown us how good the model can be using all those researchers. So let's go to the abstract. So during decoding stage, caching previous key values state KB consume extensive memory. So they are saying when we cache the KB matrix during decoding state, it consumes lots of memory for long, of course, for the long context window. Uh, Window attention, where only the most recent KB are cached, and they observe some interesting phenomena like attention sync, which is a well-known phenomena. We will see in the further slides. And they introduce the streaming LLM, again a technique that enables LLM trained with a finite length attention window to generalize the infinite sequence length without fine tuning. So without fine tuning, without any training, uh, they can have a infinite sequence length theoretically, what they have mentioned. And again, they said that we discovered that adding placeholder token as dedicated attention sync during pre-training can further improve the streaming deployment. So we will just note the points of the abstract, what they have given. So they have first point, they have talked something about KV cache. Second, they have talked about window attention. Third, attention, they called something as what they discovered is attention sync. And fourth, placeholder token as dedicated attention sync. We will discuss all these points. And then fifth, infinite sequence length without fine tuning. How can we do this infinite sequence length without fine tuning? And the sixth point is stream eval dataset. I think I haven't seen in the given in the abstract, but yes, they have given a new dataset for a long context length. Then first we will shortly go to the KV cache. Why we need KV cache on all those things. So we in self attention we multiply X with the WQ matrix, which is a weight matrix, to get the output Q. And similarly for the other rest of the thing. And in self attention we store this K and V matrix. So why do we store this K and V matrix? So let's say we have some input again. Here's our input, and we need to so we don't need to calculate this K and V again and again for the previous tokens. And hence we need to store this K and V matrix. So window attention. This window attention I have taken from the long format paper, which is some other paper. Uh, and in this paper, they haven't discussed about KV cache. What they have said ki, we can have full attention or n square full attention like this. This is the by default, I mean, general classical way of calculating the full attention. We multiply Q with K transpose and calculate whole as it is. And what they have proposed in the long form paper is we can have sliding window attention. That is, we will be just calculating the first K tokens only for the uh, so we will have a window of size K, and we will slide it like in this way, so that the we will only calculate the attention for the nearby tokens. I hope this is clear. Any questions here, till here? Okay, then let's go ahead. And what the streaming LLM has proposed, ki this dense attention, calculating this dense attention has E squared quadratic space consumption and time consumption. And the PPL, the perplexity, is very poor for the long context. Similarly, for the window attention, it has good space complexity, T into L, but still the perplexity is not good. We won't be talking about the sliding window recomputation. And then for the streaming LLM, that is theirs. And they are saying that we are getting a good space complexity as well as the perplexity.
Amod, can you go
Yes.
back to the, can you explain the matrix once?
Okay, this matrix.
Huh.
Or okay. So this is dense attention. Let me draw a diagram. So what we do is Q into K transpose in the self attention, right? So Q is made something like a number of rows. Let's say this is first row, second row, and third row. First row consists of the first token. Okay, I will give it 1, 2, and 3. So first row is for the first token, second is for the second, and third is for the third.
Hmm.
Similarly, K is also the same thing. all the key, whatever the key of the first token is in the first column. I'm talking this about the K transpose. Okay. Therefore, I am drawing it vertically.
Hmm.
And second and third. Okay.
Hmm.
When we multiply it, we are getting something like this. I might not able to draw it. 1 and 1. Okay. The first and second will be 1 and what is the relation between first token of the queue with the second token of the key?
Hmm.
1 and 3. Okay.
Hmm.
And similarly 2 and 1, 2 and 2 and 2 and 3.
Hmm.
Okay. So they have grayed out this area, as you can see, because in decoder we cannot see the future token and we don't have to see the future token.
Right.
Hence they have grayed out this area. And now uh, what they have saying, this is for the dense attention, whatever I have shown you here. Okay. So now what they have in this the window attention, what they are saying is my first token, for example, my window size is just 1. My first token will look into the previous token only. My second token will look into the previous token only. That's it. And
Hmm.
third token will be look into previous token. So when I calculate this 2 here,
Hmm.
it will just look into the previous token, which is 1. Here they have taken, I think, the window size as 3, you can say. That is,
Hmm.
I will look into the first last 3 previous token and calculate its attention.
Hmm.
Okay. So I have shown here matrix. This is our default, what do you say, K attention matrix. Okay. Um, which is calculated from Q and K transpose. Here you might see the matrix like this, but it's actually not the matrix like that. The dimension of this matrix will be number of tokens multiplied by K, where K is our window size. Okay.
Hmm.
Here the dimension of the token matrix will be n cross n, but here the dimension of the token matrix will be n cross K or n cross L. They have given L as a window size.
Hmm.
Okay. So that's why they have given the order as number of tokens, input tokens T, and L
Okay.
as the how many previous token you want to see. So they have said, okay, we want to see 4 previous token, then that's the L they have given here.
What is this ये recomputation in the third case जहाँ पे we like maybe ignore some K tokens पहले?
I haven't looked into it, so I haven't. I need to check it.
अच्छा. Also, so ये जो attention sync यहाँ पे they are showing, I don't know exactly what this is, but this is similar to having a global attention on the first token and then okay.
Like this, right?
हाँ हाँ.
You can say it is similar, but let's say I have already told that no discussion about the KV cache in this paper. S-
हम्म.
So what they say कि KV cache तो नहीं है इसमें मतलब,
हम्म.
but this paper by default means the KV cache will be included. But yes, we will look into it. What the attention sync is meant. The thing is कि you might say that this has been already done here in the global plus sliding window attention. But what these guys have given is a very detailed description about how they are doing, which the previous papers haven't given. And these guys have shown that this works like that. We
Hmm.
will check this attention sync in the further slides.
Okay. Okay. So just one clarification. So the idea of attention sync is exactly the same as global attention, right?
Yes, but just you have to include the KV cache also in it.
I got it. So maybe this is just optimizing on the cache level and hardware level, and long former mein to you will have the entire matrix. Some elements will be zero for the attention scores that we don't calculate, right?
Yes, yes, but long format does not make this matrix zero. you just calculate the the green shaded area you are seeing here. This will be the dimension of your matrix.
हाँ मतलब that's what I'm saying कि rest of the elements we don't need to compute.
Yes, yes, right. Rest of the element we don't need to compute.
Okay, ठीक है.
Okay, thank you. So window attention. Here they have given that the dense attention fails once the input length surpasses the pre-training attention window size. So in this, we will see about Llama 270. Dense attention, once the pre-training length, the which on which it has been trained on, got surpassed, then it starts giving a higher perplexity to us. So as you can see, above the 4K length, we are getting very high perplexity. And window attention collapses once the input lane exceed the cache size. Cache here, they means the KV cache. And that is the initial tokens are evicted. We will know what this initial tokens are evicted means in the further slides. And the third is keys. They are saying streaming LLM demonstrates stable performance, which is this red in the red color. That's what they have shown. Now the attention sync. The same thing has. We might have observed this diagram in multiple papers. So what they are saying is, in the basic layer, in the lower layers, the attention for the nearby tokens are more, and as we go to the higher layers, that is beyond bottom two layers, the attention is concentrated on the first token only. So there are higher values of attention scores on the first token. Many observe on in many paper this similar thing has been observed, like the lean formal. Now we will go into attention sync. Attention sync is nothing but like a CLS token in the BERT. So the CLS token has all the information of the whole context, what we say in the BERT. This is the similar thing, which we call it as attention sync. But let's understand what they are saying, their version of the attention sync. So till here, any questions? Okay, let's go ahead. To understand the failure of the attention window attention, we find an interesting phenomenon. Autoregressive LLM, surprisingly large amount of attention score is allocated to the initial tokens, irrespective of their languaging model. So what they are saying is, for the initial tokens, there is a large amount of attention score has been allocated. Despite that token can be anything. If you in the further slides, they prove it and get if we change that initial token to anything and check it, it will still have the large attention score. So then they call this phenomena as attention sink. So what they think is that the softmax operation, which requires attention score to sum up to one of the contextual tokens, uh,
आमोद
yes.
एक बार को can you just repeat your attention sync क्या हुआ?
So you are saying this red thing here, right?
Right.
These are the attention sink, what they are
Oh,
saying.
अच्छा.
I think you might have seen this in many papers of yours also.
Hmm.
during the
Hmm.
tracing or
Right, right,
something,
right.
causal
Causal
tracing.
tracing. Yeah, yeah.
Yes.
Hmm.
So that's what they are saying. This is the attention thing. And what they are saying that we observe this, something like that. And then they go to the failure of the window attention and attention sync. So they say why the window. Yes.
I actually don't understand the intuition ki why only the initial token has like more chances to has this attention score accumulation wala part.
They will be explaining in this slide
Acha, okay.
why. Okay.
Okay.
The failure of the attention window attention and attention sync. While the window attention technique offers efficiency during inferencing, it result in exceedingly high language model perplexity. So the perplexity spikes when the text length surpasses the cache size. This is due to the exclusion of the initial token. So what they said in window attention, uh, we exclude the initial token, due to which, because of, and therefore our perplexity spikes since we are excluding the initial token. That's the reason the window attention is failing. So we have to take that initial token uh, to have a better capacity. So this initial token is does not, I mean, is not dependent upon the distance from the predicate token and any such thing. That's what they are saying.
Amod, sorry.
Yes.
So
Huh.
what is this thing that perplexity spikes when the text length surpasses the cache size?
Okay. So if we can see here in window attention, once the cache size is KV cache size is exceeded, that means the initial tokens are evicted. So
Okay.
uh, let's say not here. Okay. No, this will be confusing. So let's say the initial tokens, that is this token, once I evict this from the KV cache, then our perplexity will spike.
So will I like remove all of them together from the KV cache or should I just remove the first one? कुछ least recent जैसा maybe thing we should use, right? कि maybe I let go of the first one and then bring in the nth token, then I let go of the second token and then bring in the n+1 token.
So this window attention, I mean, you what you are doing is you are just removing the last I mean, you are just keeping the recent token and you are just removing the past token.
Right. तो spike कहाँ पे होगा exactly?
Once you remove the first token, एक बार मेरा KV cache full हो गया, and
हाँ.
once you, and so when my memory is full, the problem is the KV cache is memory full नहीं होना चाहिए. ओके. सो व्हाट वी डू इज हम लोग फर्स्ट टोकन को निकाल देंगे एंड उसके बदले हम लोग रिसेंट टोकन को ऐड कर देंगे.
हाँ.
राइट.
ये जो केवी कैश का साइज है विल इट इन लाइक व्हाट इज द साइज विथ रिस्पेक्ट टू द विंडो का साइज? सो एक विंडो के सारे टोकन्स कैन दे फिट इन द कैश और उसका कुछ?
नो नो, केवी कैश का साइज इज के एन वी मैट्रिक्स का साइज. इट हैज
हाँ.
नथिंग टू डू विद द विंडो अटेंशन साइज.
नो नो, सो के एंड वी मैट्रिक्स का साइज इज ओके.
सो के केवी कैश का साइज इज जस्ट लाइक के एन वी मैट्रिक्स का साइज.
ठीक है.
सो प्रॉब्लम इज कि केवी कैश और के और वी मैट्रिक्स का साइज भी इट्स लाइक ह्यूज, नॉट अ स्मॉल अमाउंट. We have to list like n into d multiplied by number of layers, and we are increasing the n as we go by.
No, see, this is not WK matrix, right? or is this the K matrix or the WK matrix? This is
Uh,
to WK matrix, which is K.
Depend.
Yeah.
You can have a WK. W is your window, right?
No, I'm asking कि ये की वेक्टर है या की वेक्टर वाला मैट्रिक्स है, WK है या जो अटेंशन में यूज होता है?
नहीं, it's x multiplied by k. X multiplied by WK is
Equals to
equal to k. हाँ, equals to this k.
हाँ, so we are keeping K in the cache, right?
Yes, k in the cache.
हाँ ठीक है, तो फॉर every token will have a different key vector, value vector and what do I say, query vector तो ठीक है, but we are just concerned with key and the value vectors, right?
Yes,
तो हर टोकन के लिए as we go on computing this attention score we'll keep one key vector one value vector, right? तो फर्स्ट टोकन में सपोज
yes,
रख लिया, देन सेकेंड टोकन के साथ हमने रखा, थर्ड टोकन के साथ रखा, तो आई एम जस्ट आस्किंग कि ऐसे कितने टोकन्स के लिए वी कैन सेव दिस के एंड वी वेक्टर्स? इज इट द सेम साइज एज विंडो? मतलब विंडो में अगर डब्ल्यू सम पी टोकन्स है तो पी टोकन्स के लिए वी कैन सेव द की एंड वैल्यू वेक्टर्स, और इज इट
yes.
देन
It's
दैट और
same size as windows for the window attention.
ओके?
अगर
हाँ,
मेरा विंडो 1k का है तो मैं 1k तक ही रखूंगा. देन
वन के, ओके।
हाँ,
हम्म।
तो अगर आगे जाके मेरे पास इफ आई हैव मेमोरी, आई कैन जस्ट इट विल बी रिडंडेंट. I can just keep it if I have memory. But if I don't have memory, then I have to swap it with newer tokens.
राइट, एग्जैक्टली, हाँ। तो फिर हाँ, सो देन माय क्वेश्चन इज कि व्हाई डू वी सी अ सडन ऐसे स्पाइक इन द परप्लेक्सिटी? बिकॉज वी ऑलवेज हैव द जो भी कंटेक्स्ट विंडो का साइज है उतने टोकन्स का, दो कीज एंड वैल्यू वेक्टर्स वी हैव, राइट?
Uh, yes, what they are saying कि just like यहाँ पे हमने देखा कि the attention score is very huge here. Okay,
अच्छा,
so
बिकॉज ऑफ अटेंशन सिंक वी आर सीइंग दिस स्पाइक।
yes.
अच्छा अच्छा, ओके ओके, ठीक है, गॉट इट। हाँ।
क्या हुआ? Okay.
हम्म
So attention sync जब हम लोग रिमूव करते हैं for a newer token to put into KV cache,
हम्म
the spike then spike we are seeing the spikes.
ठीक है।
ठीक
एंड
है.
कैन यू शो द वो ग्राफ एक बार फिर से, सॉरी?
This one
नहीं, इससे
or
पहले।
okay.
तो ओके, हाँ ठीक है, गॉट इट। तो whenever we exceed the kb cache का size we see a sudden spike, but then उसके बाद it's almost same, थोड़ा jittery है but it's same, ठीक है।
Yes. For MPT7B, it's very jittery. I
हम्म
don't know what's the case for that.
राइट।
Let's go ahead.
ठीक है, मेक सेंस, थैंक्स।
Now that earlier question, why do LLM break when removing the initial tokens? So that's what they find. Yeah. What they find is the bottom two layers of the model constantly focus on the initial token across all the layers of the head. The implication is clear. Removing these initial tokens, KV will remove the considerable portion of the denominator of the softmax function. This alteration leads to a significant shift of distribution of attention scores from what has been to be expected from the normal inferencing setting. That's what they are saying. That if we remove this initial token, there will be a huge difference in the softmax score. And the other thing that they are saying is this initial token for each and every token that is coming, this initial token is seeing each and every tokens. Therefore, it is getting the higher attention score for that. Okay, so is this fine? Okay, let's go ahead. There are two possible explanation for the importance of the initial token.
Amod, sorry, I still don't understand why the first token is always um going to have larger values?
What they are saying is when calculating this softmax score, अगर मेरे पास कुछ that's I mean what I have read from this paper. It's there in intuition कि this जो भी स्कोर कैलकुलेट इसको सॉफ्टमैक्स को सबसे पहले जीरो तो रख नहीं सकते. दैट्स द थिंग. दैट्स द फर्स्ट थिंग. कहाँ पे तो वैल्यू डालना पड़ेगा हम लोग को.
Right.
तो कहाँ पे डालें? Then it will dump in the initial token. That's the first thing that they are saying.
ठीक है.
The second thing they are saying कि this initial token can see all the tokens. That
Okay.
is this initial token is the boss. It can see all the tokens that is coming. That's the second thing. And there are little more things also that they have mentioned in the paper that I need to recheck those things again. If you can just put this question in the Excel, I will give all the points.
ठीक है.
Acha,
Okay.
just one question here. So, softmax X, this is what is this? This is the attention score that you calculate?
Yes.
Okay.
Okay. Then they have done a testing. Why this initial token is important? So they have 2 points. The either semantics के वजह से, I mean the semantics is the main point case that initial tokens has some semantics in it, or the model has bias towards the absolute position. That's the 2 point they have. Sure. So for these 2 points, they have done a test. So they have replaced /n, that is a line break token, with the initial token, and they have made some observation. So from the observation, what they have seen that the language, the perplexity of this model is similar to the original perplexity, unless we remove this initial token. So they have tried to remove this initial token to check the perplexity, and it shown a very poor perplexity. But keeping this initial token /n is showing the same perplexity as our initial token, maybe BOS or start of sentence SOS, something like that. So they have done some calculation, I mean, test here. Without initial token, we are getting a poor perplexity attention, of course. And with the first four initial token as it is, we are getting good perplexity. First four initial token as /n, we are again getting a similar perplexity. So hence they have.
So what does this last line says? Like I understand what it is doing, but what is the intuition here? Observation?
So the observation is, if we change the initial token to /n or any other token, then the perplexity will remain the same. So model is biased towards the absolute position. So when you are removing the first token from our window attention, the model will start giving the poor perplexity. I hope I am clear.
It means that it doesn't depend on the semantics of the first word, right?
Yes.
Okay.
So
Go back
first
to the
word
previous
can.
slide. Can you go back to the previous slide?
Yes.
Okay. So it negates this hypothesis that the semantics are crucial, right?
Yes.
So semantics are not crucial. Okay.
So they are saying we can have /n or any other token for that. Just the fact is that we should not remove those tokens. If we remove those tokens, we will start getting this poor perplexity. That's the test they have done.
अच्छा आमोद, so इस absolute position के bias की वजह से then तो ideally we should also see कि अगर say instead of having the global attention score computed on the first token, we could also have like first 2 or 3 tokens, and then also we'll still see the same biasness, right? कि
Yes,
instead
they
of
have taken
having
for the first four tokens.
क्या sorry?
They have taken first four tokens.
Oh, अच्छा. And यहाँ
So
पे there is no window size, right? यहाँ पे
there is window size. This is the window plus
अच्छा okay.
1020. जैसे आई मीन विंडो साइज को मतलब थोड़ा सा वो फिक्स रख दिया उसने फर्स्ट के
हम्म
फर्स्ट फोर टोकन्स दे हैव kept as fixed.
अच्छा okay okay. And we still get low perplexity, so ठीक है
Yes.
okay, ठीक है understood, ठीक है thanks.
Now infinite sequence length. Uh, Here, what they have mentioned is let's think this is a KV cache. I mean, or let's say this is the attention. Yes. So they have kept the first four tokens as it is, like we mentioned in the last slide. So 0, 1, 2, 3. These tokens will remain as it is, and our window will be start moving. So at the initially, we are generating the 7 token. We are calculating the attention score of this whole thing, that is 0, 1, 2, 3, 4, 5, 6, to get for getting the 7 token. And when we have to evict some tokens, we won't be evicting the 0 token in this case. We will be evicting the fourth token, and then we will calculate the 8th token. So in the normal attention scenario, we will be evicting the 0 token and then calculating the 8 token. That won't be the case in this technique. In their technique, they will be evicting they will be removing the fourth token to calculate the eighth token, and further they will be removing the fifth token to calculate the ninth token, and so on. While calculating the ninth token, they will be calculating the attention for 0, 1, 2, 3, 6, 7, 8. I hope this is clear. Any questions still here?
Uh, just that this distance should be in the opposite order, right?
Distance means?
So I mean, if we are generating the ninth token, then the distance to it should be 1 and distance to 0th token would be 7, right?
Oh, no. 1, 2, 3, 4, 5, 6, 7. Yes.
ठीक है okay.
And they also mentioned, I cannot hear you. I mean, is someone speaking?
Yeah, am I audible?
Yes, now you are audible.
Okay. Yeah, so I was just asking कि let's say क्या हमारे पास let's say the prompt is कि like so prompt is like quite long, right? And
Yes.
maybe some of the words are let's say very frequent occurring words. जैसे कि let's say uh, some consonants या फिर ऐसा like we have some words जो कि बहुत high occurring है, and then there are some words जैसे noun हो गए जो कि like very which are very low occurring words.
Mhm.
So in that case, let's say कि जो attention sync होगा, so for the high occurring words, so it might be in the let's say you told about initially हो जाएगा like after first.
हाँ.
Or is it also let's say this way कि if I want to shift this attention sync for the low, जो जैसे low occurring जो words होंगे, तो उनका
Mhm.
attention sync is it also still in the like in the initial phase only, or कि उनका it might be different. Let's say if I just look at the frequency of words.
The frequency of words has nothing to do with the attention sync.
अच्छा हाँ ठीक
So
है ठीक है, so
attention
this
sync
is
is
all
for the absolute position.
right.
So they have kept some maybe random words up for the absolute position में आप रख दोगे ना, is
हम्म
first four tokens, any random
हम्म
words that won't be occur anywhere or will be occurring. It doesn't matter.
हम्म
Uh, they just keep it in the absolute position. That is the first four tokens.
हम्म
Okay.
yeah
The position they are assigning are 0, 1, 2, 3, 4, 5, 6, 7, rather than the original text position, which is 0, 1, 2, 3, 6, 7, 8, 9. That's the one more difference that they are doing. Okay. Uh, any more questions? Any other questions? Okay, then let's move to the next slide. Then evaluation. So after evaluation, they are getting the perplexity around 1 point log of 1.5. Maybe it's below 100. Yes, it's somewhere below 100 or around 50 to 70. So they are getting low perplexity for the input lengths of 4 million till 4 million for all these different models. And they have taken the dataset PG19.
Acha, Amor, just one more question. So implementation wise, the performance looks very nice, right? But
Yes.
how about the inference speed? Does it slows down the inference speed also?
Such thing I think they haven't given, but what I think about is they won't be slowing down the inference speed that much.
Like the comparison would be against the window, Windows sliding window kind of an attention mechanism.
Sliding window attention is much more faster,
Hmm.
but this I mean it's very minute just for the evicting the tokens. It will be generally same, approximately same. It won't be reducing or increasing the this speed of inference speed.
Okay. Hmm.
Uh, Then they are talking about evaluation. They have taken ARC dataset. For the dense attention, they are getting out of memory. Window attention, they have calculated the accuracy. And for the streaming LLM, they are getting I mean, very good accuracy as compared to the window attention.
So this is for
And
first four tokens? Like the first four tokens are the attention sync or even lesser than that?
for the whole paper, they have taken first four tokens.
Okay.
They haven't. They haven't tested it on different tokens. I I mean they haven't written about it that we have tested it for different first four tokens, first five tokens, or something like that.
Okay.
Um, yes. So this is what this ARC dataset will look like. This is from this paper. Think you have solved question answering. Try ARC the AI to reasoning. This is from LNAI. And then last but not the least, the stream eval dataset is their own dataset uh, for getting the perplexity of the for large context range to test out the large context range model. Um, so this is what their dataset looks like. They are just giving some numbers, and then they are querying the register containing line 0 is what. Then it should be giving the output, the desired output here. That's what the dataset they have made. Yeah, that's it. Any questions in any of the slides? There are for I have seen a GitHub page for the Gemma 2 100 million context, but they have referred to two papers, Transformer Excel and Infini Attention. For the longer, yes, for the this Infini Attention is again for computing, doing attention faster. for the long attention context length. So I need to check for these two papers in future. I may present on these papers. So any questions on this PPT or any other? If anyone wants to write the questions on Excel sheet, they can.
Sure, I will. I have some questions. I'll write there. Yeah.
Okay. Okay then. Shall we then close this meeting? Or
Maybe
anyone have
I
to?
maybe we can pick people. So Hitesh, you have any question? Hitesh, you are there? Ankit?
Yes, sir.
No, Ritesh, you are Ritesh or who is speaking right now?
I'm Ritesh.
So I was just calling Hitesh. So Hitesh, you have any questions?
No, sir.
Okay, okay, but you should have some questions, right?
Yes, sir.
So what happened? Is everything okay with you? You understood everything? Can I ask some questions to you?
No, sir.
Uh-huh. So because I had never seen you asking any question. So that means you have not understood anything.
So actually, I have other meeting. So
I can understand. Ankit?
So there were few topics like they were okay because I have studied some of these attentions.
No, but any question from the presentation?
I mean, like in one go, it's not totally understandable, but it was clear like what are the topics he's trying to explain.
So you have any doubts? You can ask if you want.
See, people who are not spending time looking into the slides, you are just wasting your time, right? Better is you just log off and do your work. Okay, so this presentations are for you only, right? So you don't have to spend a lot of time to read papers because someone has read the paper, they have understood it, and they are trying to explain. Okay, so there's no compulsion. If you want to attend, attend it. Don't want to attend, don't attend it, right? It's all fine. But if you're attending, at least be motivated to ask some questions, right? Sometimes your questions are so. Shruti has asked a lot of questions, and many of times, like I can't think of those questions, right? So I was very happy to see that some questions were asked, and they were very interesting questions, which at least like the speaker has answered very well. Right. So if you don't have time, it is okay. Don't attend. Like there is no compulsion. But this is only for you. Right. I like all these presentations, so I'm attending it. This is enhancing my knowledge a lot.
अच्छा आमोद मे बी वन लास्ट क्वेश्चन आई कैन आस्क तो फर्स्ट वाले पेपर में जहाँ पे ये कंटेक्स्ट लेंथ हुआ था तो वहाँ पे यू हैड दिस वन स्लाइड वेयर यू सेड दैट द डिकोडर विल act as the teacher and the encoder will act like a student. So I just wanted to clarify. तो यहाँ पे when we say that this decoder will act as a teacher, are we saying कि whenever we are generating कुछ भी output from the decoder will actually give the actual token which should be generated? So is that how it's acting as a teacher or is there some different mechanism?
This is the llama itself. So
हाँ
when so what is not what yeah. So when we are just disabling this cross attention,
हम्म
this
हम्म
the single model is acting as a teacher and the single model is acting as a student also. So when
when
we
we
are giving the
sorry
input,
when we disable the cross attention मतलब
मतलब उनसे जाएगा ही नहीं अगर then we can just have the single the अगर मैंने क्रॉस attention को यहाँ पे हटा दिया,
हाँ हाँ
it will be the llama only. It is nothing.
ठीक है. हम्म.
The llama का output is given to the whole this thing, the whole setup.
ओके.
Then
ओ
the single
अच्छा ओके.
model is becoming a teacher in a way, and it is a student also.
Acha, so just one question, very basic question. So what is a teacher and what is a student?
So in distilled bird, I think yes. Okay, you are asking in this question or specific?
Here itself, like maybe you can explain what do you mean by a teacher and a student?
So the llama, the instruction tuned llama is our teacher, and the student is the whole CP, the encoder, cross attention, all those things.
अच्छा आमोद, but if that is the case, then मतलब ये लामा तो will not generalize, right, to any length. तो मतलब that is not
नहीं
a
नहीं.
good teacher, right?
Yes, that's not a good teacher because it won't be having a huge context length. That's the only thing, that it won't be having a huge context length, but it is going to teach him about the instruction. I mean, in the instruction tags, there are tokens for the instruction value tuning, right? That INST tag. It will at least teach it for the tags. And in the basic, till the 4096 context length.
Sorry, I don't understand the tags वाला part.
So what they are saying कि इसको मतलब we need to make it for the instruction chat model. Yeah, this is the thing. If we want to make it a chat model, then it need to understand the tags on these INST tag, right?
अच्छा. Okay.
And here will be our chat, or let's say user, or in Llama it's INST.
हाँ
In I think GPT is for user, and then there is some I think model. I don't remember for GPT, but these are the tags. It will at least understand those tags without doing anything.
And I also missed one part. So CEPE is just the encoder wala part, and CEPED is with including the Llama
Distillation.
decoder kya?
Yes, it's a unsupervised training. That's it. Student teacher to student model, nothing else.
I mean, इससे better तो we could have just used the actual output, right?
Actual output means
I mean, जो भी हम generate कर रहे हैं, जैसे वो regular teacher forcing में करते हैं ना, तो मतलब whatever is the actual output, we pass that instead of the next generated token. तो जब x+1 token हमें generate करना है, तो we'll take the context till 1 से लेके x tokens तक, right? And x token could have been generated by the model यहाँ पे, but if we are doing teacher forcing, then we can actually use जो actual ground truth में x token है. तो यहाँ पे भी तो probably we could have done the same thing, right?
So you are saying कि we don't use a teacher student model and instead use the actual data set, something like that?
हाँ मतलब we could use that as the
We should
teacher.
have the data set, na?
But this तो is just text data set, right? So I mean, we have the data set, right?
Yes, we might have a text data set. And the thing is, this is unsupervised. I mean, we are just, we don't have the output, let's say.
हाँ नहीं. So there is मतलब what is the output यहाँ पे? It's not a label or anything, right? It's just
Yes, we
text.
don't have a label.
हाँ, so we can use this in an unsupervised fashion because whatever sentence we have, we can just give first token to the model, ask it to generate second, first or second token दिया, third token generate किया, then first, third.
Okay, you are saying कि we are giving first token to the llama and it will generate the second token like that, and
हाँ
it will learn like that.
हाँ but this is only for the answer. मतलब assume कि context plus, तो अगर वो QA वाला सिनेरियो है, मतलब QA वाला सिनेरियो नहीं आया, अंडरस्टैंड, बट context plus question दिया, then it will generate the first answer token. then
Hmm.
we'll again pass that first answer token to the model, right? And then it will generate the second answer token. Same fashion with third answer token it will generate. Then we'll give again the third answer token to the model.
You means the token by token हम लोग को
हाँ,
learn करना पड़ेगा. I don't think कि token by token learn करता है, but I need to check up on that.
हाँ, ठीक है, मे बी वी कैन डिस्कस ये बाद में ऑफलाइन.
हाँ, yes. Yeah. Oh. So any other questions from anyone else? If you have any questions, then you can write it on the Google form also.